So a bit about myself. I'm a developer on the OpenJ9 VM team. In the past, I've worked on VM support for Lambda expressions, so JSR 335. I've also worked on a Java multi-tenancy incubator project. The goal of this project was to run multiple Java applications on a single JVM instance. And currently, I'm part of the Panama experts group, where the focus is improving interop between the JVM and native applications. So the purpose of this presentation is to answer 4 questions. The first is, what is a JVM? So for those who don't know, I'll quickly go over the basics. So from how you write Java code to executing it. And for those who know, this will just be a quick background. After that, I'll talk about Eclipse OpenJ9. So I'll go over a bit about the history of the project and how it fits in with the OpenJDK ecosystem. And after that, I'll describe how OpenJ9 actually works. So in this section, I'll go into more detail about class loading, the interpreter, etc. And lastly, I'll talk about some of the cool features that we're working on OpenJ9, things we're doing to make the JVM perform better in cloud environments. So let's begin. So what is a JVM? Say you're on your favorite IDE, you write some Java code, then you press play or run to execute your code, and then suddenly the IDE spits out output. Let's take a look at what happens in the background. So the first step is basically compiling the Java source file using the Java-C compiler. So Java-C takes in a text file and produces a binary file called a class file. This is all done statically, so it's done before the application actually runs. So here's the skeleton of a class file. So this is the binary representation of a Java source file. A class file contains a single class or interface definition. So if your source file had multiple classes or interfaces, then you'd get multiple class files. The class file contains things like the constant pool, which stores things like UTF-8s, constants, signatures, class names, etc. Then it has field info for all the fields declared in the class and method info for all the methods. So in our example, we would have a method info for the main method. The method info member also has an attribute which contains the Java bytecodes. So Java bytecodes are basically machine instructions for the Java virtual machine. Bytecodes are the elementary operations used to describe behavior, similar to assembly instructions for a CPU. Since the class file contains bytecodes and not machine code, it means that the class files themselves are platform independent. So you can run a class file on any platform that the JVM supported on. So this is where we get the write runs run anywhere from. This is a bit from the side, but the previous slide shows that the JVM doesn't actually care about the source code, it cares about bytecodes. This means that any language that compiles a Java class file can also be run on the JVM. So examples are Kotlin, Groovy, and Scala. So the previous steps show how we go from a source file to a class file. The final step is running the application. So if you were doing this command line, you would type the Java command, possibly give it class path arguments or VM options, and then give it the main class name. IDEs do this for you in the background. So the Java command launches your application in the Java runtime environment. So we'll take a look at the JR8. So the Java runtime environment includes everything you need to run your code. So this is the JCL, the base class libraries. This includes things like Java-Lang system, the Java util concurrent package, Java-Lang math, etc. The JVM is a computer machine that runs bytecodes. So it's composed of natives, JCL natives. So these provide the low-level system functionality for things like opening file sockets, closing files, etc. It has the class loader, which is responsible for loading classes, linking, and it also triggers verification. The verifier ensures that the code is well-formed and follows the standards specified in the JVM spec. And then the interpreter and the JIT are the bytecode execution components. So the interpreter basically has routines that execute each bytecode. And the JIT is a dynamic compiler that compiles the bytecode into the platform-specific code. The garbage collector is essentially a memory manager responsible for memory allocations and recycling. And at the base level is port and thread library, which is an abstraction layer over the platform-specific system calls. This is a very high-level description. It's a little more complicated than this, but for this presentation, this is enough. So now that you have a basic idea of what a JVM is, we'll take a look at OpenJ9. So Eclipse OpenJ9 is IBM's open source JVM. It's based on the closed source IBM J9 JVM. So while the project is about 8 months old, it's based on a JVM that's been used for many enterprise products since 1997. The Eclipse OpenJ9 has an EPL v2 license, as well as an Apache 2.0 license. EPL v2 has a secondary license that makes it compatible with GPL. So this means that the project is very open and very easy for anyone to contribute. So how does OpenJ9 fit in with OpenJDK? So this is an overview of the JDK. As you can see at the top, we have the Java language itself, and beneath that are tools like Java C compiler, Java P disassembler, the jar class archive. Then after that is the UI toolkits, so things like Swing, AWT. Beneath that are the base class libraries, and at the very bottom is the JVM. The default JVM that comes with OpenJDK is Hotspot. OpenJ9 offers an alternative JVM that you can also use as part of an OpenJDK binary. So how does this work? The idea is basically to take out Hotspot from OpenJDK and replace it with the OpenJ9 JVM. This picture simplifies things a bit, as there are places where the two VMs don't cleanly map over each other. So building OpenJDK with OpenJ9 requires some patches. The patches themselves are not many. We're talking about thousands of lines of code versus millions of lines in OpenJDK itself. Most of these patches are make file changes, configuration changes, and there are minimal JCL changes as well. So these are temporary until, so most of the patches are temporary until we've upstreamed our patches to OpenJDK. Until then, our goal is to keep them as minimal as possible. So what are the steps in building OpenJDK with OpenJ9? So as you can see, this only requires a slight modification to what you would normally do with OpenJDK. The first step is cloning an extensions repo. This is basically a mirror of OpenJDK minus Hotspot. And then the get sources step fetches source for OpenJ9 and OMR, which I'll go over later. And after that, you run configure, and then you make. The link at the bottom has more information on how to set up your environment for building OpenJ9. But if you don't want to build OpenJDK yourself, there is a project called Adopt OpenJDK. This site provides pre-built JCK verified binaries. So you can currently get a Java 8, Java 9, and Java 10 binaries for different platforms. It includes OpenJ9 as well as Hotspot binaries. So if you're a JVM implementer, this is a good open source project to be a part of, and it's great for the community. So how does OpenJ9 work? This diagram is similar to the previous conceptual diagram I showed you before, but there are some differences. OpenJ9 implements some of the core JCL classes, things like Java-lang object, string, thread, class loader, and a few others. The reason why OpenJ9 implements its own version is that these classes are closely tied to the JVM implementation. So they don't work with the OpenJDK classes, and as a result, we have to implement our own. Another addition is RAS tooling. RAS for reliability, availability, and serviceability. So this is basically a diagnostic component built into the JVM to make it easier to debug the JVM as well as applications. So it includes things like the trace engine for tracing internal function calls as well as Java method calls. It includes automated verification checks for the GC heap and checks for memory allocations done by the JVM, so it checks for underflows and overflows. So this is a very useful feature for debugging in general. So a number of years ago, the IBM JVM team embarked on a new project to create a runtime toolkit called OMR. This project is based on the realization that a large part of language runtimes have language agnostic components. So what this means is that there are parts of the JVM that don't actually care about the Java specifics. They could work with other language runtimes as well. So as a result, the IBM JVM was split into two projects, OMR and IBM JVM, which we get OpenJ9 from. So in the current OpenJ9 JVM, we have the Java GC part and the OMR GC. The Java GC is the language-specific stuff, like object layout, root set scanning, how to walk the stacks. And the rest of the functionality, things like marking, sweeping, allocating objects, all of that stuff lives in OMR GC. Likewise, the Java JIT includes the machinery to understand the Java bytecodes and convert into IL. Things like IL construction utilities for trees and nodes, code generation, things like that live in OMR JIT. And OMR also includes the thread and port library, since these are basically OS API wrappers. So one of the goals of OMR is to support other language runtimes, and there have been experiments with MRI Ruby and CPython. The benefit of a project like this is that any improvement made in OMR the benefits of that can be reaped by other language runtimes. For example, if OMR JIT adds support for a new vector instruction, all other language runtimes built on top of it get that support. So to quickly summarize, OMR provides building blocks for building a runtime. It lets developers build new runtimes without constructing everything from scratch. So now we'll go back and take a look at some of the core components of OpenJ9 JVM. So previously, we looked at how JavaC takes a source file and generates a binary class file. And we looked at how the class file contains bytecodes for each method. Class files are very densely packed, so this is great for footprint, but it does make it difficult to find the pieces of information that you need. So as you'll see here, class files have many non-uniform repeating types, things like the constant pool, field info, and method info. They're like arrays with differently sized elements. So in order to find the method, you have to walk the entire class file up until that point. You can't directly index the method. So this is not something you want to do every time you call a method. Ideally, you'd layer a structure over this so that the interpreter and other parts of the runtime can operate efficiently on the data. So learning from our embedded Smalltalk VM background and the experiences with that, OpenJ9 splits the class file into two parts, ROM and RAM. So ROM in this context basically means not written after loading. With embedded VMs, this would be done in link time, so you could actually put the ROM classes in ROM memory. But nowadays, we load the class structures and we don't write it after that. So the ROM class keeps track of symbolic data in the class file, things like UTF string literals, bytecodes, primitive constants. And the ROM class attempts to remove all variability from the class file. In some cases, this is not possible, as I'll show you later. But for most of the data, we're able to do this without variability. Also, the ROM class is position independent, so it can be mapped anywhere in the memory space. So this is what a ROM class looks like. On the left is the J9 ROM class structure. It only has symbolic info, so just names, no live types. And all the variable data is moved below. So unlike the class file, where sometimes you have to walk the entire thing to find anything you want, with this structure, it's much easier to directly index and find data. So on the right is what it looks like in memory. So there's the J9 ROM class structure, followed by the ROM constant pool. The ROM constant pool is also fixed size, so we can directly index the ROM constant pool, unlike the class file where you have to walk things. And beneath that are the interfaces, and then beneath that are the J9 ROM methods. The J9 ROM methods are variable sized. They start with a header, which describes the name and signature, the number of arguments, and then beneath that is the bytecodes. So because methods can be of different length, the ROM methods themselves are variable sized and do need to be walked. But we can index directly to the beginning of the ROM methods, so it's still an improvement. So you may have noticed that the J9 ROM class structure only has two types, the U32, which is an unsigned 32-bit integer, and a J9 SRP, which is a self-relative pointer. So we'll look at how those work. So in typical applications, a pointer is the address of a location you want to dereference. So a pointer points to the target. So an example is on the left. At memory location 30, we have a pointer to memory location 50. And if we want to get what's at 50, we simply dereference it. However, an SRP is a self-relative pointer. So it's relative to its own position. So if we want to dereference an SRP to get the target, we take our own address and add the value in the pointer, and that is the address we dereference. So the benefit of SRPs is that they are position independent. All of the data is relative, so the structure can be mapped anywhere in memory space, and it still works. So in this slide, you can see that moving a structure with a regular pointer means that you have to update all of its pointers. In our case, this is not possible since it's ROM, so we can't write it again. But with an SRP, this is not an issue. We can move the structure around, and all the pointers still point to the correct place. Another benefit of SRPs is that it helps us keep the sizes smaller. Since we only need the relative difference, we don't actually have to be able to address the entire memory space. If we know that the target pointer is going to be a certain distance away from where the pointer is stored, and if we have guarantees about that, then we can limit the size. In OpenJ9, SRPs will never be larger than 32 bits, even if you're running with a 64-bit JVM. So up until now, we've focused on symbolic and constant data. Now we'll look at the rest of the class file. So there are bytecodes that have dynamic properties to them, invoke virtual being one of them. This poses a challenge because we don't want to look up a method each time. As previously said, a ROM class is a ROM, so we can't save the resolved method in ROM class. And we don't want to repeat lookups over and over again. So for this, we use RAM classes. So RAM classes are basically the live representation of the class. They hold real pointers and object references, and they're always fixed location. The RAM classes describe how the class is represented in the specific instance of the JVM. So it's possible to load the same class file in two separate JVM instances, and they'll have two different shapes. In one case, the superclass may define a field that doesn't exist in the other case. So the RAM class always represents how the class is in the current JVM instance. The process of building a RAM class requires that you load all superclasses and interfaces beforehand. Once they've been loaded, then we calculate the size of the vtable, and we calculate the size of the offsets. One of the side effects of this design approach is that we can't do things like bytecode quickening. So this is patching your bytecodes at runtime. Since the bytecodes are loaded in the ROM class stage, they're fixed. So at that point, we can't modify it. The only exception to this is if you're running with JVM-TI agents. So in this case, you'll be able to do redefinition on the class. This is made possible because we can actually take a ROM class and convert it back to a Java class file. So here's what a RAM class looks like on the left. So as you can see, it has real pointers. There's some object references there as well. So the RAM class is basically a cache to hold resolved values. The vtable holds resolved method references. So on all subsequent invocations, there's a faster invocation path. Likewise, with the RAM constant pool, it holds class refs, field refs, method refs. So all the resolved values go there. So when you do an LDC instruction, we don't have to resolve it each time. We just pick up the cached copy. The J9 methods have fields that point to the bytecodes in the ROM method. So it's easy for us to access those. And they also have counters to keep track of method invocation. So this is something that we do for profiling. So up till now, we've looked at the native types. Here we'll see how they correlate to the Java types. So on the heap, we have types such as Java-lang class and Java-lang class loader. These types contain hidden fields. Hidden fields are regular Java fields, except they cannot be accessed by Java code. So only the JVM knows about it. So a Java class has a hidden field that is basically a pointer to its RAM class. And likewise with the class loader. So by keeping the native types off heap, off the Java heap, that is, they'll always be in the same location. So it's easy to modify and access it without worrying about pointers moving. The J9 class loader contains class segments where all the RAM classes and ROM classes are stored. It also has a class table where the key is the class name and then the value is the RAM class. So it makes operations like class for name very fast because we simply do a constant time lookup for the class in the class table. So this design where we have a Java type that has a mapping to a native type is something we do a lot of, and as you'll see later with Java-lang thread. So now we've looked at class loading, we'll take a look at how code actually runs. So the ROM and RAM class slides show how we get bytecodes into runtime. To look at how they get executed, we'll first look at threading. So on the native side, at the bottom, we have ORMR thread. This is essentially a wrapper around an OS thread. By using ORMR thread in the thread library, we have a single API point that we can use on all platforms. So creating a thread on Windows uses different API than it does on Linux. The ORMR thread API abstracts over all those differences, so it makes the code a lot cleaner and a lot simpler. Above that is the J9 VM thread. The J9 VM thread has a one-to-one mapping with the ORMR thread. The main purpose of the J9 VM thread is to keep track of the interpreter state, which I'll talk about later. The J9 VM thread also has a circular linked list that connects it to all the other J9 VM threads on the JVM. This is important because it lets us send signals to all the VM threads. So being able to send signals is important for things like halting all the other threads if we want to GC. And on the heap, we have a Java-lang thread. The Java-lang thread has a one-to-one mapping with the J9 VM thread. So it's very similar to the case with the Java-lang class and the RAM class. The Java-lang thread has a hidden field that points to its J9 VM thread. So OpenJ9 uses a cooperative threading model. This means there's no preemption. So threads can be in one of the following states. They can have VM access. So this is a state that allows the thread to run Java code. The thread may release VM access if it reaches a synchronization point or if it does an operation that may block. So things like transitioning to JNI may release access, or class loading may release access. The other state is exclusive access. So exclusive access means that only that thread can operate on the JVM. So this is typically used by the GC master thread during a GC cycle. And then there are the Java thread states like wait, sleep, and blocked. So these correspond to the operations that you can do in Java-lang thread, like thread.sleep. And then there's the halted state, which is the state of all the threads other than the exclusive thread when you have a thread with exclusive access. So now we'll take a look at the interpreter. As I said earlier, the JVM is a computer machine that executes bytecodes. The interpreter is one of the ways that bytecodes are executed. There are over 200 bytecode instructions currently specified in the JVM spec. And the interpreter implements a routine that simulates each one, which is why it's a virtual machine. So similar to native applications, the interpreter has its own stack to run bytecodes. The interpreter also has its own PC, has its own SP to point to the top of the stack. So the OpenJ9 interpreter used to be written in assembly generated from a Smalltalk framework. This was a big barrier for development, as well as for open sourcing it. It kind of made the learning curve a lot steeper because you had to learn Smalltalk and then you had to learn how the framework worked. So we actually started slowly phasing it out since Java 7. We started replacing it with a C++ interpreter. As of Java 9, the VM is completely C, C++, and some bits of assembly. So it's much easier for external people to understand. So how do threads and the interpreter interact? Each J9 VM thread is basically an interpreter instance. So it maintains state to describe the execution of that current thread. So it keeps track of interpreter variables like the SP, the PC, the method. So the method is a pointer to the current J9 method. As I said earlier, the J9 method points to the bytecodes. So it's just one more step and we can get to the bytecodes. The PC points to the currently executing bytecode. And on the right is the Java stack. So basically, the frames are laid out such that the args go first, then the temp variables, and then the frame. The frame describes how to get back to the previous frame. And then above that are all the pending pushes for the next method call. So the SP points to the lowest live value on the stack, and the A0 points to the first argument in the frame. Most of the time, these interpreter variables are actually in registers. So we're not constantly writing it back to the thread structure. We keep them in registers until we might lose VM access. So until there's a possibility that we might halt execution. When that happens, we write it back to the thread. And when the thread resumes, then we restore the state back. So this is one way to execute bytecodes. Now we'll look at another. So JVMs have a component called just-in-time compiler. In OpenJ9, this is called a testarossa JIT. So JITs are dynamic compiler, meaning that they compile code at runtime. So they take bytecodes, generate assembly for the specific platform. But that kind of simplifies things. Another way to look at a JIT is as a high-performance runtime collection system. So it takes in inputs and it produces outputs. So one of the inputs that a JIT takes is profile data. So things like whether a path is taken all the time, or maybe a path is never taken, or how often are backward branches taken. Is there one implementer of this abstract method, or are there multiple? How many times is a method called? So things like this. Profiling is done by both the JIT and the interpreter. So there is a JIT sampling thread, which periodically samples how much time is being spent in the method. And the interpreter keeps track of how many times a method has been called, so the invocation count. And the JIT may also embed profiling counters in generated code. The other input is runtime environment and configuration data. So this is basically the static information about the system. So things about resources, like how many CPUs you have, how much memory is available, what processor are you running on, is this instance debug enabled, did the user specify max compilation threads, what is the object layout. So that sort of static information is also an input to the JIT. So the first step in compiling is generating an IL tree from the bytecodes. So this is done by the IL generator. So here's an example of how it works. On the left, we have the bytecodes. So the IL generator splits it into expressions. So the first 4 bytecodes form an expression, and you can see it in the orange box. So each bytecode maps to an IL node. So the IL generator creates a tree that represents that expression. So everything on the right is an operand to things on the left. So as you can see, the inputs are loading the A and B, and then providing it to the add operation, and then storing that. So each expression gets a tree top, and this procedure repeats for all the bytecodes. So eventually we get something that looks like this. We have a bunch of tree tops, all representing expressions, all linked. So that's basically the method. So once the IL tree is created, then it's passed to the optimizer. So the optimizer's job is to optimize the IL tree. It does this by performing analysis on the profiling data and the static environment data. So the profiling information lets it know how to optimize, what things to optimize, and how much to optimize it. So the optimizer performs optimization passes on the IL tree. So it might do the first pass to simplify the tree. Next pass might do monitor elimination. Next pass might do another optimization. It may add speculative paths and provide fallbacks if assumptions are wrong. So once the tree is optimized, it's passed on to the generators. So this is where things like register allocation is done. It's where the instructions are picked for each operation based on the platform. And after that, it generates machine code, which is fed back into the runtime. So it's not just machine code that's fed back into runtime. Also, there's some metadata that's fed back, things like GC maps. So it describes which registers hold references, so that when a GC occurs, we can find where all the references are. So the test roster JIT does tiered compilation, meaning that it has different levels of compilation. So when a JVM starts, all methods run interpreted. So this is basically the first level. After they reach a certain invocation count, or the profilers determine that a lot of time spent in the method, then this get compiled. The cold stage is not heavily optimized, but it does perform the compilation step very quickly. The warm stage performs more optimizations, but takes a little longer. And likewise with the hot stage. The profiling stage generates optimized code, but it also adds in profiling counters. And the final stage is the scorching stage, which does the most optimizations, but also takes the longest to compile. So typically, we increase the compilation tier as so the methods that spend the most time executing on JVM tend to be more heavily optimized because these optimizing to a high level does take time. So we've looked at how we run bytecodes. Now we'll take a look at objects. So different JVMs have different sizes and layouts for the same object. Things that tend to determine the size of an object are things like field and array element sizes, object and field alignment, the specific JVM mode, whether you're on 32-bit or 64-bit, if you're using compressed refs or non-compressed refs. So here is a table. At the top, we have the primitive types, and on the side, we have the second row is the size in the field, and the third row is the size in an array. So as you can see, in an array, booleans and bytes are all 8 bits, shorts and chars are 16, ints and floats 32, and longs and doubles are 64. However, in a field, anything that's 32 bits or smaller is 32. So this is basically a trade-off. We could pack fields in instances, but that means that if you have a small field followed by a large field, then you have potential for misalignment. So this is a decision that basically trades footprint for performance. So as you may have noticed, there are no references in this table, and that's because the size of a reference depends on what JVM you're running and what mode you're running in that JVM. So there are JVM implementations for 32-bit and 64-bit execution modes. The difference is how they represent memory addresses. So on 32-bit JVMs, pointers are, a memory address is 32 bits, so referencing an object is 32 bits. And on 64-bit JVMs, memory addresses are 64 bits. So ideally, we would always use 32-bit pointers, but 32 bits limits you to a 4 gigabyte range, and nowadays it's not uncommon to get heaps going to 100 gigs or even larger. So 64-bit JVMs give us more range, but they do double the size of references. So ideally, we want something that kind of combines the best of both of those. So that's the third option. Before I get to that, I'll quickly talk about alignment. So generally speaking, a Java object is allocated with a minimum guaranteed alignment boundary. In OpenJ9, this is 8 bytes. So the interesting thing about guaranteeing an alignment boundary is that if you have an 8-byte alignment boundary, it means that all references, for all references, that at least 3 significant bits are always 0. So this is important because it potentially gives us 3 bits to work with. Since we know that those bits will always be 0, we can use it to store extra information. And in this case, we use it for extra addressing bits. So a technique is to store a larger pointer in a smaller pointer by shifting it down and discarding the zeros. So 64-bit JVMs offer an alternative mode called compressed references that does exactly that. This mode stores all references in 32-bit pointers, either using 3-bit shifts, which gives you up to a 32 gig range, or 4-bit shift, which can give you up to 64 gig range. And of course, 4-bit shift requires that you have a 16-byte alignment. So running with compressed refs with shift enabled does have an impact on throughput. However, this is a net positive because the objects get smaller, and because objects are smaller, object locality is better. And because you're using less memory, it decreases your GC frequency. So using compressed refs is actually an improvement over using the 64-bit mode. So here is a picture that shows the ranges. So at the top is the theoretical limit. So with 0-bit shift, which is basically a 32-bit pointer, you can go up to 4 gigs. With 3-bit shift, you can go up to 32, and with 4-bit shift, you can go up to 64. But in reality, we don't actually go up to those limits. Not all of the heap can be used. So not all of the heap can be stored in the smaller memory space because we need to store things like class data, which also has to be within the 4 gig range. And the JIT also stores metadata in the 4 gig range. So typically, if you run with compressed refs, if you're under 2.5 gigs, we won't do any shift, so it'll be a 32-bit pointer. And if you're over 2.5 gigs, then we'll do 3-bit shift. And if you're over 27 gigs, we'll do 4-bit shift. And that goes up to 57. So these are the typical defaults. They do vary from platform to platform, but this is what you can expect. So as you probably know, JVMs decouple the problem of memory management from application logic by providing garbage collectors. This means that programmers can avoid things like memory leaks and dangling pointers. So a GC has 3 main goals. It allocates space for new objects, it identifies live objects, and it reclaims space occupied by dead objects. Some of the techniques, or the 3 techniques used by OpenJ9 JVM are mark sweep. So the mark phase marks all live objects, and the sweep sweeps everything else, everything that's dead. The second approach is mark sweep compact. So this is basically an extension on mark sweep. So this, at the end of the sweep, it also compacts, so it moves all the live objects together. So this is good because it decreases the fragmentation that you would normally have with just a mark sweep. And then the third approach is a copying collection. So this is with GC policies that have different regions. So you basically copy all live objects from one region to another, and you mark the old region as free. So here's a table that shows all the collectors that are offered with OpenJ9. So at the top are tracing collectors, so opt throughput, which is the typical stop the world collector, and opt average pause is a concurrent collector. And then there's GenCon, which is a generational collector. So this is the default collector that is turned on when you run with OpenJ9. This is good for small and medium-sized heaps. There's also balanced GC, which is a region-based collector. So typically, it splits the heap to over 1,000 regions, 1,000 smaller regions. So this is really good for large heaps where it can do partial GCs in one region. And then there's metronome, which is incremental collector. So metronome comes from our previous hard real-time collector that was used in hard real-time VMs. So metronome has very small incremental GCs. So the pause times are very small, which means there's low latency for the application. So it's really good for soft real-time applications. So Charlie's doing a talk tomorrow, and he'll go over this in much greater detail. So we'll be talking about the GC policies that OpenJ9 offers. So if you're interested, I encourage you to go to his talk. All right, so now that you have some idea of how OpenJ9 works, we'll go over some of the features, some of the more interesting features of OpenJ9. So earlier we talked about how classes are loaded in the JVM, how we go from the class file to the RAM class and get the RAM class. So let's say, for example, we have 3 JVMs all running the same code on the same machine. Perhaps this is a service where you have multiple instances. In each of them, when the classes are loaded, you have to parse the class file, then create the ROM class and the RAM class. So basically 3 things to note. The conversion takes time. Parsing a class file takes time. Creating the ROM class takes time. The second thing is it always produces the same result. So in each case, you're always going to get the same ROM class. And because the ROM class is positional independent, it means that you can actually use just a single ROM class and share it between all the JVMs. So OpenJ9 offers a feature called shared class cache. So basically, when a shared class cache exists, a JVM can connect to it. So a shared class cache is just an area of shared memory on the machine, and it's of fixed size. So when a JVM connects to a shared class cache, instead of looking on disk for the class, it looks at the cache first. And if it finds the class, then it loads it. We use certain heuristics to ensure that the classes are the same. And if those heuristics fails, we compare with the new class to see if it can be used. But the goal is always to use the cache if the class exists there. So the benefits of this are that it improves start performance because we don't have to parse the class file and we don't have to create the ROM class. We get to running code much faster. Also, it does come with footprint improvements because we're sharing ROM classes. We have less duplication. And obviously, the more JVMs you're running, the more your footprint improvements are. So the shared class cache is not just for classes. It can also be used for dynamic AOT. So the shared class cache can store precompiled AOT code, as well as profile data from previous runs. So when a class is loaded, it already knows which methods are hot, which assumptions are likely to be true, previous optimization steps. So this is a big benefit because it reduces the ramp-up stage that JVMs typically have. It typically takes time for the JVM to get to peak performance, but with AOT, you can get to that point a lot quicker. So it's typical to see that turning on shared class cache can reduce footprint by about 20%, depending on the number of JVMs you're running. And it can also improve startup time from 10 to 30%. So using a shared class cache is very simple. You just have to add the shared classes command to your VM options. If the cache exists, it will connect to it. If it doesn't, it'll create one. The cache will persist beyond the lifetime of the JVM. So any JVM started after can use it. And there are also options to set the size of the cache. By default, it's a 16 meg cache, but you can set a larger one if you like. Because the cache can persist, it has to detect if the class on disk has been changed. So it does this by detecting file system updates. So if the timestamp on the file has changed, then the JVM knows that this class has potentially changed on disk. So it will do a comparison. If the class is different, then it will update it in the cache. And all of this is done transparently. So all you have to do is add the option, and the rest is taken care of. Some of the limitations are that the JVM can only connect to a single cache at a time. And the cache is unique to the JVM type. So if you launch the JVM, if you created the cache with a 64-bit JVM, you can't use it with a 32-bit JVM. And the other thing is that the cache can't grow. So once it's full, it's full. If you need more room, you can destroy the cache and create a larger one. So now we'll take a look at another feature. So the Xtune virtualized is another option to improve JVM performance in resource-constrained environments. So it's typical for cloud deployments to under provision. So here's an example where the hardware only has 4 cores, but each container believes it has 2. So in this case, you really have less resources than you think you have. So the Xtune virtualized option modifies the JVM to reduce the amount of resources it consumes. So it reduces the amount of CPU it uses, as well as it tries to minimize its memory footprint. So the option modifies the JIT heuristics to lower the compilation time, usually about 25%. And it modifies the GC heuristics to not aggressively expand, as it normally would. So this reduces throughput, sometimes up to 5%. But in cases where you are resource constrained, this is a benefit. So the Xtune virtualized option also turns on another option called idle detection. So in a lot of transaction-based Java applications where the model is request response, you may get a lot of requests coming in, and then the request frequency might dynamically change over time. Also, you have big data applications that may use a lot of resources during peak loads and then not as much an off-peak. So this can lead to spikes in memory usage and dips. So typically what happens is during active phases, you allocate objects, and as soon as you can't allocate, then you GC. But if you reach an idle phase before you get to the point that you GC, then you're actually holding on to all that garbage during the idle phase. So for businesses that run applications with consumption-based pricing models, this is not good. This means that when you're not doing anything, you're still paying for all that memory that you don't need. So there's some approaches to use to add logic to applications or use external agents to kind of detect when the application is idle and then trigger a GC. But this kind of shifts the burden to the developer, and it's hard for external applications to understand the intricate details of the JVM heap. So OpenJ9 offers an option that basically monitors the JVM to determine when it's idle. So it looks at the CPU usage and other internal heuristics to determine if the VM is actually working or not. When an idle state is detected, it checks to see if there's a lot of garbage on the heap. And if there is, it triggers a GC. An additional benefit of this approach, in addition to reducing footprint, is that by triggering a GC during the idle phase, you delay when the next GC will happen. So in the best case, you may not have to GC at all during the next active phase. So this greatly improves throughput. Here is another feature called JIT as a service. So previously, I talked about the shared class cache, which allows dynamic sharing of AOT code. This is an experimental feature right now. It's not yet released, but we're currently working on it. And we're hoping to have demos later out in the year. But the idea is that you basically decouple the JIT from the JVM. So in cases where you're deploying the same application, multiple times, perhaps you have multiple instances of a service, and it's quite typical for cloud deployments to under-provision their containers. So you may not have many CPUs on your specific container. So by decoupling the JIT from the JVM, you save on footprint because the JIT has its own scratch memory for compilation. The JIT itself needs memory. So there's an obvious benefit with footprint, but also it means that you don't have to compile the same method over and over again. Once the JIT has compiled it once, every JVM connected to it can get access to it. So, so applications can get compiled code much faster, and they can get to peak performance much quicker. Another potential benefit is that by moving the JIT to a separate process, you can give it more resources. So a lot of times the JIT will back out of an optimization because it runs out of memory or it takes too long. If the JIT isn't a separate process, you can give it more memory because you're still making savings by not having it on each JVM. And you can potentially let it work on optimizations longer. And every JVM that's connected to it gets the benefit. So as I said, this is an experimental feature, but we hope to have some demos of this later in the year. So to quickly summarize, OpenJ9 is a new open source JVM that runs with OpenJDK. It has many features that make it appealing for cloud environments. We try to minimize footprint and improve startup. We're also currently working on new features to make this even better. So if you're interested, come try it out and let us know what you think. So that's it for my talk. If you have any questions, I can take them now.
Thank you. You said that OpenJ9 has cooperative threading model. Does that mean that a single thread with an endless loop can hang an entire JVM?
Yes, so in theory, a single thread with an endless loop could. But it also depends what you're doing in that loop. If you do have anything in your loop that could reach a synchronization point, so any object allocation or anything that might trigger class loading, then there are places where you would be able to release access.
Yeah. Hi, thanks a lot for your talk. I have a question on the slide about idle tuning GC. So in this slide, you say that you trigger GCs when the VM is idle, but on your chart, the native memory goes down, but the Java heap not on the next slide. So shouldn't the Java heap?
So the Java heap here, this line represents all the live objects.
Okay.
So we're not counting what is garbage in this case. So that's why the process memory, the total memory for the process goes down, but not the live part.
Ah, okay. So the blue includes also
the
Java heap. Okay, thanks. And just quick second question. As far as I understand, you had the bytecodes in your ROM classes, right?
Yes.
So when you do debugging and you have to patch the bytecodes, how does this work?
So with debugging, you're typically using a JVM-TI agent.
Okay.
So with what we're able to do is we can, with the ROM class, we're able to generate back the original class file. So you can patch the class file and then reload the ROM class. And that's how we do
and then it's
JVM
not shared
support.
anymore between the instances, or is it not? They're not shared anymore?
Yeah. So the retransform class is not shared.
Okay.
Yeah.
Okay. Thanks.
Hello, and thank you for the great talk. My question is about profiling, and you said that for profiling you use data from JIT, data from interpreter, and also sampling and hardware counters. My question is, why are you using sampling? Because isn't it enough to use just data from JIT? You can just use instrumentation, and isn't it enough?
So sampling is typically done before we've even JITted the method. Sampling data is one of the early stage profiling data. So this is, sometimes the method is really large, and you spend so much time in the method that the invocation count is really low, but you are spending time there. So that's why we use the sampling thread to figure out how much time we're spending there.
All right, and how does this sampling works? Do you sample on save points or something?
So I'm not the expert on the JIT side, but typically the sampling thread is woken up periodically. There's some heuristic that determines how often this happens. And it looks at the threads and looks at how much time is spent in each method. It doesn't pause execution. So this is all done concurrently while the application is still running.
Thank you. And maybe one more question about JIT as a service.
Yeah.
You said that when a method is compiled, it can be used by any JVM that uses JIT as a service. But usually JIT use some optimizations that are based on profile, and in different JVMs there can be different profiles. And so is it okay to use the same compiled method in different JVMs in such scenario? Maybe you want to recompile it because the profile is different.
Yeah, so the benefit of JIT as a service is that you can collect profile data from multiple JVMs. So if you've determined that these two JVMs are really running the same application, it means that you don't have to profile all the time. If one JVM has already done the profiling data, then you know it applies to the other JVM. So it's a bit selective in how it will compile each method. But the idea is that you're leveraging the work done by one JVM so that the other JVMs can benefit.
Hi. I have a question about garbage collectors. Can you define what is a large heap?
So large heap is typically something around 100 gigs, around that range.
Thank you.
Okay.
So maybe the last question.
Thanks a lot for your interesting talk. There is a lot of information. I'm not sure that I were able to grasp it all, but it's my fault, not yours, of course. And my first question about ROM and RAM classes.
Yeah.
Well, you mentioned there are a lot of benefits from using it, but it's always a trade-off. What kind of overhead do they introduce comparing to hotspot? For example, if I am a heavy user of a lot of classes, proxies, and so on and so forth, how much overhead ROM and RAM classes introduce?
Sorry, can you describe your scenario again? You're a heavy user of proxy classes?
There are a lot of different classes loaded in my JVM.
Okay.
So if it is not so many classes, then the overhead is minor. But if there are a lot of different classes, of course, it grows and grows. And what kind of overhead? It is in percents.
Oh, okay. So I can't give you a number. This is something I'll probably have to profile myself to determine what it's like. But this is not something that you can avoid. I'm not sure how exactly Hotspot loads classes, but I imagine they do take the class file and transform it into some internal representation. And I imagine they're keeping track of the same data that we are with ROM and RAM classes. What we've done is we've divided basically all the constant part between the live part, because this enables sharing. But in both cases, I still think you need to keep track of the same amount of data. So it's hard for me to answer the differences there.
Okay, my another question about optimizations. And well, there are different optimizations in Hotspot, and ClickClick calls them heroic optimizations, such as bias locking, for example. What kind of optimization does J9 have?
So again, I'm probably not the best person to answer this. I do know, so like the J9 JIT does, I think, what you typically expect. So it does a lot of monitor elimination where it sees it can get away with that. It has the typical loop and roll superword vector optimizations. We do a lot of speculative optimizations as well. Recently, we added OSR, so we are able to make assumptions and constant fold things, and then if these things change, we can jump back and decompile. So yeah, I'm not a JIT engineer myself, so I'm not sure of the specifics, but yeah, I think we do have some presentations. If you look at the OpenJ9 page, there are some presentations by some of the JIT developers that go over the specifics.
Okay, and my last question about Terra Rossa JIT.
Mm-hmm.
Well, you said that there are a lot of profiling information. Is it exposed to a developer? Can I look, for example, at the profiling information with aid of JMX, for example, of some kind?
No, so that stuff is not exposed at that level. I guess if you really wanted, you could use our dump viewer. So this would be after execution, or you can generate a dump at runtime as well. But with that tool, you can look at the internal structures to see what the internal counters. So to see things like how many times the method's been run, what compilation tier the method's currently at. But there are no easy tools like JMX tools for getting this information.